Okay, so welcome to the second course of the second week, and we have Adam on to give us this particular lecture. Again, this, as you learned in Luke's lecture, as he rightly pointed out, that you begin with something which is a test particle, but then you have to take into account in the real world, the body has its own gravitational field, and therefore that will modify what happened, what has been sort of treated in the first chapter. And this turned out to be a fairly complicated kind of problem, as you would see, because again, Adam started his PhD work working on this particular problem, and he tells me that what is required for the LISA project probably will take another 15 years. So what I really want to point out to you is that this is an activity where there is an experiment which actually requires you to push the theory to its limits, because only then you can extract out the best physics from the experiment which is really going to happen. So the self-force problem in the context of LISA is one such problem which has really been in development for the last couple of decades. I remember that when I started working on the post-Newtonian stuff, the self-force problem was just sort of being started. But still, there is a long way to go. So as you see in this lecture, there will be sort of opportunities for younger people like you to contribute to this particular area. So please follow those lectures very carefully. Adam.
Thank you. Okay. So I'm going to start kind of the opposite way from how Luke started. He started with broad GR. I'm going to start with the motivation. Why are we doing what we are going to do in the following lectures? So the motivation is the systems called compact binaries, where you have, say, a neutron star or a black hole, and another one orbiting around each other, and they emit gravitational waves. These gravitational waves carry off energy and angular momentum out of the system. So these two things gradually spiral in towards each other and then eventually merge to form a single black hole or a single neutron star, potentially, if these are two neutron stars. So these kinds of systems are what have been observed by LIGO, and if you're interested in LIGO nowadays, you can actually go and look at the live alerts. You get public alerts every time there's a potential detection, and it happens almost weekly now, I think. But LIGO has only been observing very particular kinds of compact binaries. So we look at the parameter space of binaries. This is the orbital separation, so the distance between the two bodies. And then down here, I'm going to have the ratio of the two masses. So say this is little m and this is big M. Then there are three key areas of this parameter space. So there's one case where the separation is very large, so you're going high up here. And then, but say the masses are roughly equal size, so little m is same size as big M. Then there's the case where they're near together and still roughly equal size. And then there's the case where one is much, much bigger than the other one. So in different regions of this parameter space, you need to use different modeling methods to develop an accurate model. And Luke will go in depth in what's called post-Newtonian theory. So up here, the leading approximation is just Newtonian gravity, where these are following Keplerian orbits. And then you look at relativistic corrections to Newtonian gravity. Down here, where these are about to merge, you use, well, really the only thing that works is full numerical relativity, where you just put the system directly into the full nonlinear Einstein equations and you solve it numerically. And the idea is that as this in-spiral happens, a single binary will move down from the post-Newtonian regime into the numerical relativity regime. And so early in the in-spiral, you can use post-Newtonian theory. Late in the in-spiral, you use numerical relativity. And there's also something called effective one-body theory that kind of patches these things together into one single description. Okay, but this is the region that I'm going to be focusing on for this entire course. And down here, we use gravitational self-force theory. So I'm going to get into that, what that is, in a little while. Let me first say what the experimental ramifications are of this. So use different modeling methods in the different regions, but also different experiments will be able to observe different regions. So the frequency of a binary is related to the total mass and it's basically just the Keplerian formula for frequency. So it's related to the orbital separation and the total mass. So let's look at the case where the orbital separation is comparable to the total mass. So these things aren't too far apart from each other. Then this formula for the frequency just becomes 1 over the total mass. So the frequency scales inversely with the total mass. So what that means is, well, actually, that's not useful to look at this. I'll get back to that in a second. Okay, this is with geometrical units. Let's put in some dimensionful quantities. So if you restore gravitational constant and speed of light, this is what it looks like. Now, different detectors are sensitive to different frequencies. So ground-based detectors, like LIGO and Virgo, are sensitive to frequencies around 100 hertz. So what does that mean about the total mass if we invert that formula for the mass? It means the total mass is about 10 to the minus 2 seconds c cubed over g. And if you put in the values for those constants, this is 20 solar masses. So the total mass that LIGO is sensitive to is about a few tens of solar masses. And that's why the detections that have been made have all been a few tens of solar masses. Now, that means the LIGO or other ground-based detectors are not going to be able to detect these things with very extreme mass discrepancies, or not discrepancies, ratios, where one of the masses is much, much bigger than the other one, because in order for us to detect a binary, we need both of the masses to be at least a solar mass, So the biggest mass ratio you can imagine happening here is roughly 1 to 10. Big M over little m can't really be bigger than 10 or so. But LISA, the space-based antenna that's going to launch in 2034, is sensitive to a totally different frequency band. So rather than a few hundred hertz, it's sensitive to frequencies in the millihertz range, so 10 to the minus 3 hertz. So what does that imply about the total mass of a binary it can detect? It's about 10 to the 5 solar masses. So at least I can see much, much, much more massive systems than LIGO can. So you can imagine looking at two different types of systems. One is still the kind of comparable mass binary that LIGO detects, but now both masses are huge. So that would be where little m is roughly the same size as big M, but both of them are extremely massive. So these are called supermassive black hole binaries. So these are, of course, very important sources for LISA, or they will be, and a lot of work is going to go into modeling those. But again, you're still using full numerical relativity to model them. You're not using a totally different modeling method. So that's one type. But the second type is where, okay, the big mass is of order 10 to the 5, but the small mass is just of order 1 or a few tens of solar masses. So these are the systems over here on the right side of this parameter space, and these are the systems that I'm going to be focusing on. And these are called extreme mass ratio inspirals, or just EMRIs for short. Okay, so why are EMRIs interesting? Well, they're a unique regime of the two-body problem, so they're theoretically interesting. But they're also unique probes of highly relativistic physics. So let's draw that picture again with some more parameters. In general, the central black hole is going to be spinning with some spin j and this mass capital M. The smaller body is also going to be spinning with the spin s and mass little m. And the big mass is not going to move much because the smaller mass doesn't have that much gravitational attraction to pull the big mass. So really, you can just think of the small mass orbiting around the big mass. These kinds of systems will occur at the centers of galaxies, where you'll have a supermassive black hole, and you'll have a whole bunch of smaller objects orbiting around. Every once in a while, one of the objects will get kicked into a tight orbit around the big black hole, spiral in, and eventually fall into the big black hole. most of those we expect the smaller object to also be a black hole, but it's also possible for it to be a neutron star. But the supermassive object is definitely not a neutron star. It's almost certainly a black hole, or it could potentially be something more exotic. Now, the interesting thing about this is these orbits do not look like nice, simple Keplerian orbits. They're actually extremely complicated. So they don't just go around like that. They're also going up out of the plane, and they're also precessing very rapidly, and they're also highly eccentric. So they're a big, ugly mess. So they have actually 3 different frequencies. One is just the azimuthal frequency going around and around. One is the radial frequency going in and out between a maximum and a minimum. And one is a polar frequency as it goes up and down through the equatorial plane. So generically, we expect highly eccentric orbits. Whereas LIGO sources are all essentially circular orbits. We expect inclined relative to the equatorial plane. And again, that's different than LIGO sources, which tend to have either aligned or anti-aligned spins, which then restricts them to planar motion. And as I said, they have 3 frequencies. So they're called tri-periodic. So they're not exactly periodic in the sense of having a closed orbit. This orbit generically never closes in on itself. But the spectrum is tri-periodic. It has 3 base frequencies, and all the other frequencies are just integer multiples of those base frequencies. Okay, not only is this highly complicated, with a lot of intricacy in the orbits, it's also very long-lived. So little m spends a huge number of orbits of order this mass ratio, so about 10 to the 5, in the very strong field region around M. So I'll come back to why this time scales like this with the inverse mass. But the key thing is that because it's executing this highly intricate orbit and is spending a long time doing that, it's acting as a really precise probe of the space-time around the big black hole. So it's an incredibly accurate probe of the strong field region. And then all that information is going to get encoded in the gravitational wave, and then we can extract all that information by analyzing the waveform. So once we have an EMRI waveform, we get a lot of information from it. And incredibly precise information relative to other experiments. So we'll be able to measure the mass and the spin of the big black hole to around 0.01% relative uncertainty. So 10 to the 4, maybe 10 to the 5 significant digits in our measurements of the parameters of the big black hole. You can also measure the higher moments. So in particular, the quadrupole moment of the big black hole. slightly less accurately, but still to well below 1% error. Now, how many of you know the no-hair theorem? Basically everyone, okay. So in GR, we're told that a black hole in vacuum, in asymptotically flat spacetime, is completely characterized by its mass and spin. It doesn't have any other degrees of freedom. And so in particular, all its higher moments are uniquely determined by its mass and spin. So the Kerr geometry has a full set of multipole moments, but every single one of those is simply related to mass and spin. So if we're able to measure the mass and spin and the quadrupole moment, we can then test the no-hair theorem. Or really, more precisely, we can test whether this is actually a Kerr black hole. So if it's not a Kerr black hole, then either GR is wrong, or it's some other more exotic object than a black hole. So that's certainly not what we are expecting. We're expecting it to be exactly a Kerr black hole, and this will allow us to constrain possible deviations away from the Kerr geometry. So this is probably the biggest goal of things we can get by measuring waveforms from EMRIs. You can also measure other types of deviations away from GR. You can test whether there's an event horizon around the black hole. You can test whether the dynamics conform to GR dynamics. And typically, the measurements of these deviations away from GR for an EMRI will be at least an order of magnitude more precise than any other proposed experiment. So it's really incredibly precise information you can get out of these EMRIs that you cannot get in any other way. You can also get a lot of astrophysical information because different astrophysical scenarios will lead to different characteristic parameters of these EMRIs. You can measure the mass function, which is the number of black holes for a given mass. You can even do cosmological measurements. You can get the Hubble constant. You can do a lot of things with these. Okay, but all of that relies on having extremely accurate models of the waveforms. If you don't have those models, then you're not going to be able to get this insane precision because you're going to be limited by your model. So this is especially important for EMRIs, more important than it is for most other sources of gravitational waves, because EMRI waveforms are actually really, really weak. So the waveform is typically completely buried under noise. So say you have this complicated EMRI waveform. So this is the strain as a function of time. This is going to be buried under noise that's, well, here I'm drawing it as if it's 2 times bigger, but it's typically orders of magnitude bigger, usually about 1 order of magnitude bigger. So the noise is much, much more pronounced than the actual waveform, much stronger than the actual waveform. So we need to dig the true waveform out from inside the system of noise. And now, LISA data analysis is also much more complicated than LIGO data analysis. So for LIGO data analysis, you typically have a signal, nothing happens for quite a while, you have another signal, and you just need to find one signal at a time. LISA data analysis, you're going to have many, many signals all at once. So you're actually going to have the number of EMRIs you're going to be able to find, the estimates vary by quite a lot, but you're probably going to have a few tens of EMRIs in the course of a 2-year lifetime for the LISA mission, and they're going to extend over basically that entire 2 years. So they're all overlapping. They're all in the data all at once. You're also going to have those supermassive black hole binaries, which are not just 10 times bigger than the EMRI signal, they're thousands times bigger. You're also going to have tens or hundreds of thousands of white dwarf binaries in our galaxy that also create detectable signals. So all of these things need to be modeled all at once in order to, well, do other things, but also in order to get the EMRI waveform out from underneath everything else. So much precise information encoded in this waveform because of the way the EMRI is sampling the space-time around the big black hole. So to get this information out of the data stream, though, we need to be able to match the phase of this buried waveform over its entire lifetime. So we need to get those precise measurements. So not just measurements of the mass and spin, but also all the parameters of the actual orbit and the little mass and the little spin. So there's many parameters in the system. So to get precise measurements of these parameters, we need much, much less than 1 radian of error in our waveform. Over that entire lifetime of 10 to the 5 orbits. Because the way this signal is dug out is using matched filtering, where you integrate the entire data stream against your model waveform. And if you're out of phase, you're not going to be able to get any coherence in that matching. So we need an error that's much smaller than a radian over hundreds of thousands of wave cycles. So it's an extremely high accuracy we're aiming for here. Okay, so how are we going to do that? Well, first, what can't we use? So we can't use post-Newtonian theory. Because EMRIs are very relativistic. So post-Newtonian theory is not accurate enough. We can't use numerical relativity. So there's actually a few obstacles to using numerical relativity. One is that you have very disparate length scales in your system. So you have a small length scale corresponding to the size of the small object. Then you have the orbital length scale, or the mass of the big black hole. And you need to resolve these different length scales simultaneously, which is computationally very expensive. But then the bigger issue is the long time scale. There's just way too many cycles or orbits. So typical numerical relativity simulation that people run right now, you'd have maybe a few tens of orbits. I think the most that's ever been done is 500 orbits, but that's something they just left running for like 6 months straight. Whereas we need 10 to the 5 orbits. So there's no way numerical relativity can cope with that. Also, the number of time steps you need in each orbit goes up as the mass ratio goes up. So the width of a time slice, or the size of a time step, is basically constrained by the size of the smallest scale in your system. So not only do you have a number of orbits that scales with 1 over the small mass ratio, also the number of steps per orbit scales with some power of 1 over the mass ratio. So it's just hopeless to do this with numerical relativity. Yeah. What fraction are outside of the post-Newtonian regime? Inside, probably none. It's in the strong field regime as soon as it enters the Lisa band. It's already shrunk a lot by the time it's got into the Lisa band. Yeah. Because they're eccentric, so they're getting deep into the potential of the big black hole. So I think post-Newtonian theory can probably help. I'm hoping that it can help with EMRI modeling, but in a kind of constrained or confined way. Maybe I'll mention that later. Yeah, so because of the high eccentricity, even if it's weak field over here, it's strong field there. So it's actually, in addition to have shrunk a lot by the time it gets into the Lisa band, it's also lost a considerable amount of its eccentricity by the time it enters the Lisa band, but it's still really eccentric compared to LIGO systems. So you can expect up to like 0.7 eccentricity. So the data analysis people will have a noise modeling. I have no idea how they do that. I mean, LIGO also models its noise. I don't know how they do that either. So if it's randomized noise, then the matched filtering will kill off the effect of the randomized noise. Certain things that might appear to be noise, and they're actually called confusion noise, are not genuine noise. Like the many thousands of white dwarf binaries create, things that are not random noise in a signal, and those do need to be modeled properly. There's nowhere else we would know of that has such large black holes. There's been some discussion of maybe you could have a 10 to the 4 solar mass black hole in a globular cluster, and you could form EMRIs there. But so what masses are you talking about? So 10 to the 3 is not extreme enough. The 10 to the 3 would typically be called actually intermediate mass binary. So as I was saying, in globular clusters, people have looked at extreme mass ratio binaries around 10 to the 4 solar mass black holes. Those are much less studied in the case of EMRIs than in the galactic nuclei. So the astrophysical modeling has been done less, and also our models will be less accurate if the mass ratio is smaller, or depends whether if the masses are more similar. So the focus has been on the galactic nuclei, and they can't be active galactic nuclei, they need to be clean galactic nuclei. I don't think I'm qualified to answer that. So certain things will not be, but I think that then they'll just actively model and model particular systems to find out what it is. I don't know enough about the global data analysis schemes, and the data analysis schemes are still in the process of being worked out. So because it's a totally different challenge than LIGO data analysis, so need to develop new data analysis methods. Okay, so we can't use the main things that have been used in the past, post-Newtonian numerical relativity. So what do we use? As I mentioned, we use what I called gravitational self-force theory. And in this context, that is basically just a particular variation of black hole perturbation theory. So we use black hole perturbation theory. Slash self-force theory. Okay, so what is this? Essentially, we take the exact metric of the system, and we assume we can write it as an asymptotic expansion, where we have a leading order metric. So this is the metric of the big black hole. Take that to be the Kerr metric of the big black hole, capital M, plus smaller corrections. So I'm going to take this epsilon to be the little mass over the big mass, that mass ratio. So we'll have perturbations to the metric. We'll have first order perturbation. We'll have second order perturbation, and so on to higher order. And oftentimes, I'll think of capital M just defining what I mean by order 1 quantities. So we can think of epsilon as just being the small mass. Okay, so we have a metric that looks like this. And then, say this complicated world line I drew, we'll have an equation of motion. So say we have little mass tracing out some trajectory or some world line, which I'll call gamma. It has coordinates, which I'll write as Z alpha. And so it's tracing out this path in the Kerr background. Then this world line will have an equation of motion. This is the Kerr metric of the big black hole. Yep. This is just the exact metric describing the two-body system. Yep. So this is exact two-body metric. So the equation of motion for this world line will have the form of a covariant acceleration. Have any of you not seen this notation for covariant acceleration? Okay. So the covariant acceleration will start at order epsilon. This is first order force per unit mass, or first order acceleration. And so on like this. So there's no 0th order term, there's no term proportional to epsilon to the 0. And that is what Luke was just saying, that at 0th order, the motion of a small test object is just geodesic in the background space-time. So for a geodesic, You just have 0 here. And that's a geodesic of the Kerr background spacetime. So all these corrections are coming from the fact that your small object is gravitating. It's producing its own gravitational field that then influences its own motion. So we call this the self force, because it's the force on the small object due to the fact that the object is gravitating. We'll get into more details about what appears in each of these terms. But the first question you need to ask before diving in to finding out what H1 actually is and what F1 actually is, first question is, how high order do you need to go in this expansion? Okay, first, I'm going to justify that time scale I mentioned of 1 over the mass ratio. So how am I going to do that? I'm going to look at the rate of energy loss. So the small object loses kinetic energy at the same rate that gravitational waves carry energy out of the system. So in a leading order approximation, gravitational waves carry energy away, and all of that energy is coming out of the kinetic energy of the small object. So the rate of change of energy is of order, or is proportional to the gravitational wave flux of energy, and that is proportional to h dot squared, the time derivative of h squared. Have you encountered a formula of this form before? Just from basic gravitational wave analysis? Okay, good. So in our case, that's epsilon squared. So h is order epsilon at leading order, and so this flux is epsilon squared. But the energy itself that we're talking about was the kinetic energy of the small mass. So that's just proportional to the mass itself, which is, again, proportional to epsilon. So the relative rate of change of the energy is E dot over E, and so that's epsilon squared over epsilon, which is just epsilon. So this defines for us a characteristic time scale of change of the system. The rate at which the small object is spiraling into the big object. So that's the time scale is 1 over the rate. So E over E dot, that's 1 over epsilon. If we want to make it have the correct dimensions, we'd have capital M squared over little m. And this is called the radiation reaction time. Physically, it's just the amount of time you need to pass for the energy of the orbit to decrease a significant amount. And it's a very, very long time because it's 1 over the small mass. Okay, now let's use this time scale to figure out how accurate we need approximation to be. Just to give it the right dimensions, we know it's got a little m at the bottom. So to give it the right dimensions, it's got to have 2 lengths on top, and the only other length scale in the system is capital M. So it's got to be capital M squared over little m. But again, in these systems, you can always just think of capital M as being order 1, and you can just think of epsilon being little mass, and you don't need to worry too much about dimensions. Okay, so how accurate do we need this equation of motion to get to meet our accuracy goal of having a very small error in the phase of the system after this timescale? So let's suppose that we just use F1 over there, and we just drop F2, and we drop F3, and so forth. We just use F1. So suppose we know F1, but not F2. Then the error in the acceleration is, we use delta to denote error. Is now epsilon squared, because we're dropping the second order term there. And that corresponds to an error in the position that I can get just by integrating this in the most naive way, just bringing a t squared up to the right-hand side. So the error in the position of the smaller object scales as epsilon squared times time squared. So after a radiation reaction time, where the time was 1 over epsilon, this t squared cancels the epsilon squared, and we have epsilon to the 0. So epsilon to the 0, it could be small if for some reason the numerical coefficient is small, or it could be huge. But typically, we can imagine it's going to be of the order 1 radian, and we need our error to be much smaller than 1 radian. So this error in the position is going to translate into an error in the phase in a basically 1-to-1 fashion. Say this position is the azimuthal position of the orbit. Then that directly corresponds to the phase of the waveform. So if we have an order 1 error in our position, we also have an order 1 error in our waveform, and that's too large an error to accept. So that means we cannot drop F2. We need to keep F2. But if you follow through the same reasoning, you can see that you don't need F3. So having F1 and F2 is necessary and sufficient. That's what we need in our waveform model. So that means we need first order perturbation theory and second order perturbation theory. Okay, so this is the ultimate goal of EMRI modeling, to be able to calculate first and second order effects, calculate the in-spiral of the orbit, and calculate the waveform that comes out to that accuracy. So I'm going to try to cover as much as I can every aspect of the modeling problem that goes into this. So going from the most foundational aspects to more practical aspects. But with only 5 lectures, that's not enough time to cover everything, or even close to everything. So if you want more detail, there are now a large number of reviews. And so I'll mention the most recent one and the one that's pitched at people with the least expertise in EMRI modeling. So that's a review from last year by Barak and myself, with an archive number 1805-10385. So this covers basically every aspect at an informal level, so it doesn't get very technical, but it covers everything. So I'll recommend that if you're interested in more details. Okay, but now I have the context laid out, the motivation for doing what we're doing. Now I'm going to take a step back and start at the lowest level, the most foundational aspects, and then build up as we go. Yeah. So they'll generally live the entire lifetime of the mission, so 1 or 2 years. Sometimes they can plunge before the mission ends, but they're very long-lived. So we're usually interested in modeling on the order of 1 year. And those supermassive black hole binaries, where you have 2 supermassive black holes, they also are long-lived, but they only complete a small number of orbits in that time. No, there's way too many orbits in it. So in addition to the problem I mentioned of just computation time, you'd have to, if you ran a current simulation for 10 to the 5 orbits in numerical relativity, it would be running way past the time when LISA launches, and way, way, way past that, and keeps on going to the end of the century. It would take forever. But it's not just that that's the problem, it's also that if you have a small error in each orbit, that can accumulate. So by the end of your 10 to the 5 orbits, you can have a huge error. And that's actually what was going on with that integration I did over there. So you imagine a small error of order epsilon squared in each orbit, but then it integrates up to a large error after the whole evolution of the system. Okay, so I'm going to start off with just general perturbation theory in GR. When does this lecture end? 1. Okay. Okay, so suppose we know, or suppose we have a metric an exact metric of a system that depends on some parameter epsilon. So this is what I was writing before as a G where the loop doesn't close in on itself. But I've found in the past that when I try to write this, I invariably write that a lot of the time. So I'm going to put a tilde on top to indicate the exact metric rather than try to write it like this every time. So the tilde is the exact metric as a function of some parameter. So it can just be any parameter here. In our case, it's going to be the mass ratio, but for the rest of this lecture, it's just completely general. Now we want to approximate this metric in the case that this parameter is much, much less than 1, so a small parameter. So the most obvious thing you can do is just write down a Taylor series. So then the exact metric is the exact metric evaluated at epsilon equals 0 plus epsilon times the derivative, and again evaluate at epsilon equals 0 plus a half epsilon squared times the second derivative, again evaluated at epsilon equals 0, and so on. So if it's a smooth function of epsilon at epsilon equals 0, you can write out this Taylor series to arbitrary order. So this quantity here, the exact metric evaluated at 0, I'm just going to write as g alpha beta without the tilde on top. This quantity here, the derivative with respect to epsilon, I'm going to write as h1 alpha beta. And this quantity here, let me move the order here, epsilon squared, a half. So this quantity here, including the factor of a half, I'm going to write as h2 alpha beta. So now we have the same kind of expansion we had over here. We have g alpha beta plus epsilon h1 plus epsilon squared h2. And because this looks like a prime, let me keep putting parentheses around those numbers. So the actual metric perturbation, or the asymptotic expansion we use in self-force theory, is not quite a Taylor series, but it's the same structure as a Taylor series. So let's just focus on the Taylor series case. So the things I had written down here, h1 and h2 and so forth, they actually depend on epsilon in a very specific way. So in a Taylor series, the coefficients of powers of epsilon are always independent of epsilon. But have you ever looked at singular perturbation theory or more general asymptotic analysis? So in more general problems, a Taylor series can either just go wrong or give you a bad approximation, and then you look at more general kinds of series you can write down. And the self-force case is a more general series where the coefficients depend on epsilon in a prescribed way. And I should cover some of that later. Okay, let's define the total perturbation. H alpha beta, just to be the difference between the exact metric and this zeroth order metric, which we always call the background metric. So I'm just going to define that difference, and you can see from the Taylor series that this is just the sum over positive n's of epsilon to the n h n alpha beta. So this is just summing up all the perturbations. Another way to say this is that g tilde, the exact metric, is the background plus the perturbation. The perturbation is given by this series. Okay, so now we want to substitute this into the Einstein equation and get a sequence of perturbative Einstein equations for the perturbation. But I'm going to build up to that over the rest of this lecture. So the exact metric, g tilde, satisfies the exact Einstein equation, which I'm going to write as g alpha beta constructed from g tilde. So this means the Einstein tensor I'm looking at is the one corresponding to g tilde, is equal to 8 pi t alpha beta. So then the question we want to answer is, what equations does hn alpha beta satisfy? So to get there, for a while I'm going to work just with the exact Einstein equation, but I'm going to rearrange a few things. So we'll start by writing this exact Einstein equation which I'll call star, as an equation for this H alpha beta that includes all the orders of perturbation in it. Okay, it'll take a few steps even to get to this. So first thing to note is that this G is constructed from G tilde. That comes from the Riemann tensor constructed from G tilde. So the first thing we want to look at is writing down this Riemann tensor in terms of a piece that only involves G, the background, and then another piece that involves H, the metric perturbation. So this comes from something else. It comes from the definition of the covariant derivative. In particular, it defines the commutator of the covariant derivative. So I'm putting a tilde on top of covariant derivatives to mean the covariant derivative that's compatible with G tilde. So the Riemann tensor is essentially this commutator. So that means we can take another step back and say that this covariant derivative comes from G tilde. So we want to build our way up through there. Start with G tilde, get something for the covariant derivatives, get something from the Riemann tensor, finally get something for the Einstein tensor. Okay, so I'm going to define a tensor C alpha beta gamma such that the covariant derivative compatible with the exact metric minus the covariant derivative compatible with G. So this is compatible with G tilde. And this is compatible with the background. This operator, when it acts on some vector W, is equal to this tensor C, contracted into that same vector for any vector W. Now we can also write this tensor as the difference between two Christoffel symbols. So C alpha beta gamma is the Christoffel symbol associated with G tilde minus the Christoffel symbol associated with G. So let me show why that's true. So the proof that this tensor is equal to this difference is fairly simple. So we've got C alpha beta gamma omega gamma is covariant derivative tilde of, actually I guess I'm going back and forth between calling it omega and W. Let's stick with omega. Omega alpha minus the background covariant derivative of omega alpha. Now let's write that in terms of Christoffel symbols. This is partial derivative of omega alpha plus gamma tilde alpha beta gamma omega gamma. minus, again writing this in terms of Christoffel symbols, the partial derivative omega alpha, now minus the background Christoffel symbol, contracted into omega gamma. So partial derivatives just cancel out. All you're left with is this difference between Christoffel symbols of the full space-time and the background space-time, contracted into omega gamma. So this is true for any omega. Therefore, it follows that this thing here has to be C alpha beta gamma. Now, you might wonder, how is this a tensor when we've got Christoffel symbols, which are not tensors? But there's a general statement that the difference between two Christoffel symbols is a tensor. So this is well defined as a tensor. So you can kind of brute force that and just look at how each of these transforms under coordinate transformation and see that the non-tensorial terms cancel out, so therefore must be a tensor. Or you can prove that more formally. Okay, but now I'm going to write down a more explicit version of that C, the Riemann tensor and then the Einstein tensor. So an explicit version of this C is 1/2 G tilde alpha mu times the background covariant derivative acting on H plus the background derivative acting on H with the indices swapped around. So here I'm just interchanging beta and gamma. Minus one more covariant derivative. Now you might recognize that this looks similar to the formula for a Christoffel symbol in terms of derivatives of the metric. So let's prove that. So if we choose a local inertial frame, meaning a frame that's inertial with respect to the background. So say choose Riemann normal coordinates of the background. In this local inertial frame, the Christoffel symbols of the background are 0. So in this frame, C alpha beta gamma, if we look at the definition, or not the definition, but the result over there, that is the difference between the Christoffel symbols. In this frame, it's just Christoffel symbol tilde associated with the perturbed metric. So now let's just write down the formula for the Christoffel symbol in terms of derivatives of the metric. So now we have partial derivatives, not covariant derivatives. Same exact structure we had up there. So partial derivatives of G tilde. Now let's use one more trick. So this is equal to 1/2 G tilde alpha mu. And now I'm just going to replace these partial derivatives with covariant derivatives compatible with the background. All right, can anyone tell me why I'm allowed to do that? Right. Christoffel symbols are 0. So therefore, the covariant derivative in this local coordinate system is identical to partial derivative. Now, one more thing is that each of these terms here is the background plus the perturbation. But the covariant derivative that's compatible with the background, when it acts on the background term, just gives 0. So therefore, I can just replace each of these g's here with h's, because the covariant derivative of g is 0. So that just gives me this thing I was trying to prove over here. All right, so now we have a formula for what's essentially the correction to the Christoffel symbols due to the perturbation. Now let's write down the formula for the Riemann tensor in terms of that. So the exact Riemann tensor is equal to the Riemann tensor of the background. So R with a tilde on top is what I was writing before as the Riemann tensor constructed from G tilde. And this is the Riemann tensor constructed from the background metric. This is our alpha, beta, gamma, delta, just constructed from the background metric. And then we have corrections coming from this C. So we have 2 times covariant derivative anti-symmetrized over these 2 indices of C itself, plus terms, or plus another term that is a product of C with itself. Is everyone familiar with the square brackets for anti-symmetrization? Is anyone not familiar with it? No? So it's anti-symmetrization, in case anyone is not familiar. You just take this, multiply by half, and then subtract a half times the flipped version. So you have a half gamma delta minus a half delta gamma. Okay, so let's prove this identity. So by definition of the Riemann tensor, our tilde alpha, beta, gamma, delta, contracted with an arbitrary vector, is equal to the commutator of the covariant derivative acting on that same vector. And we can now write each of these covariant derivatives in terms of the background covariant derivative plus that tensor C. So 2 covariant derivatives we can write as background covariant derivative acting on background plus this tensor C. So here, this term here is just replacing this covariant derivative of omega with the background covariant derivative plus C. But then I also need to replace this outer covariant derivative with a background plus a C. So now we get two C terms, because this is a rank 2 or rank 1 tensor that this covariant derivative is acting on. So we pick up two Christoffel symbols or two C's. There's the first one, and the second one. So now we just take the difference of something, or exactly this, and the same thing with the gamma and delta flipped. So the commutator, gamma, delta, tilde, gamma, nabla, gamma, tilde, nabla, delta, tilde, acting on omega alpha, minus the same thing with the indices flipped. Is now just this minus itself with gamma and delta flipped. So that's a simple calculation. We got 2 gamma, nabla. Let me write this intermediate line as just twice the antisymmetric piece of these two derivatives. So that means I just need to look at the antisymmetric piece of this quantity here. And that gives you the antisymmetric piece of this, plus the antisymmetric piece of that, and so forth. And with a couple lines, you can get down to our alpha, beta, gamma, delta, omega, beta. So this first term is coming just from the pure background covariant derivative terms. So this is nabla, nabla, minus nabla, nabla, gamma, delta, delta, gamma, acting on omega beta. So you'll have one term like this that just gives you the background Riemann. Then you have some C terms. This covariant derivative is only acting on the C, not on the omega. And some more C terms. And a couple of these will cancel. So you see, this term is identical to this term, except the gamma and the delta are flipped. But it's antisymmetric, so if you flip it, you pick up a minus sign. And so that exactly cancels that. Then we have one final term, which is the C times C term. So it's important that these terms canceled because they involved the derivative of omega, and we want to be able to cancel the omegas. We want something that's true for any omega. And so we need ultimately to be able to cancel the omega here with the omega here and just have a formula for the Riemann tensor itself that doesn't depend on omega. So it's crucial that these derivatives of omega canceled out. So we have just something that's multiplied by omega, not a derivative of omega. So what we have left here, the C product term and the derivative of C, if we cancel those omegas, gives us exactly this term, or this formula here. So I encourage you to work through the remaining steps that I skipped in going from this line to that line. It should be fairly straightforward. Okay, so that's the Riemann tensor. What appears in the Einstein tensor is the Ricci tensor. So from that Riemann tensor, we want to contract two of the indices to get the Ricci tensor. So the Ricci index beta delta is exactly that Riemann tensor, but just contracting over the first and the third index. So we just need to go over here. First term we're going to get is just the background Riemann by contracting those indices on the background. Sorry, we're going to get the background Ricci by contracting the indices in the background Riemann. And then we're going to have this alpha contracted with that gamma. We're going to have this alpha contracted with that gamma. So what comes out of that? So we just have the background Ricci plus 2 nabla alpha C alpha delta beta plus 2 C alpha mu alpha C mu delta beta. So what is the Einstein equation? So the Einstein field equation is G is 8 pi t, but G is just the trace reverse of R. So we can write G tilde alpha beta is R tilde alpha beta minus a half G tilde alpha beta, G tilde mu nu, R tilde mu nu, all equal to 8 pi t alpha beta. So this is an Einstein equation written in terms of the metric perturbation H. So we have background terms plus terms that are involving H. So this is an exact version of the Einstein equation, but written in terms of this difference between the perturbed metric and the background metric. But one subtlety here, if you go back far enough, over here, we don't just have H in our perturbation of the Christoffel symbols, we also have the inverse of G tilde. So the inverse of G tilde is not just background inverse plus H. That's not true. What is true at linear order is that you just have a minus sign there. And you can work out what this is as an expansion in powers of H to any order. Now a convention that we're going to use is that indices are raised and lowered not with the full metric, but with the background metric. So they're raised with the inverse background metric, and they're lowered with just the background metric itself. So what's meant by H alpha beta with indices up is G alpha mu, G beta mu, H mu nu. So once you've done an expansion like this, you don't have an exact Einstein equation in this form, but you can get it to any power in H that you like. Okay. Let me just say one more thing before we wrap up. So we want to expand this equation. Expand the Einstein equation. Ultimately, in powers of epsilon, we want to put in that Taylor series. But let's continue working with a full H as long as we can. So let's define for a tensor f. So any indices on here that's constructed from G plus H, or from G tilde. Let's define a bit of notation that we'll use. Delta n of f constructed from H is 1 over n factorial dn d lambda n run out of room here. Right on the next line. 1 over n factorial times the nth derivative with respect to lambda. The lambda is just a placeholder parameter of g plus lambda h evaluated at lambda equals 0. So the linear delta, just delta f, that's actually exactly the variation that Luke was using. It's just a variation of a quantity with respect to a small deviation, lambda h. But the key thing here is that, okay, so just delta f is automatically going to be linear in h. Delta 2f is automatically going to be quadratic in h. Delta 3f, and so forth. But except for this overall 1 over n factorial, you can just think of them as derivatives. So delta is one derivative, delta squared is two derivatives, and so forth. And we're going to use this to work out the expansion of the Einstein equations, I guess, tomorrow? Okay. All right, that's it then for now. Thank you.